Okay, we're done with question 6. We're moving on to question 7. In question number 7, we're going to use our GeoGebra program to help us analyze and hopefully make a conjecture about a figure that they're asking us to make. So here's what they're asking us to do. They want us to open up a GeoGebra document. They want us to create any four-sided object. So I'm going to create a polygon that is a four-sided figure. So it doesn't really matter what it looks like. It's any four-sided object. So it can be like this. There's our quadrilateral. Next thing they asked us to do is to find the midpoint. Now we can find the midpoints by using our midpoint tool. So we go and we find the midpoint of every side. And then they want us to connect those midpoints with a segment. So I'm going to connect those midpoints with a segment between 2 points. They say to go in order from E to F, then F to G, and then from G to H, and from H to E. If we create this figure inside of our quadrilateral, they want us to make some observations about the figure that's in the middle. So regardless of the figure that I change my original quadrilateral to, whatever I make that shape, and obviously if I get too extreme, it gets a little bit funky looking, but if I keep it in the general context where it's a nice convex polygon, then the figure that's inside of there appears to be something that is, well, something we've been studying here lately, and that would be a parallelogram. So sometimes it looks like a rhombus, other times it looks more like a rectangle, other time we probably could make it look like a square, but in any case, whatever we have in here, whether it's a rhombus, rectangle, or a square, we know that it will be a parallelogram. So that's the conjecture that we're asked to make, that if we were to connect the midpoints of any four-sided figure, quadrilateral, then the resulting figure on the inside, which may not be the worst idea to try to highlight those in a different color, that this thing on the inside is guaranteed to be a parallelogram. So that's our conjecture that we're making. So if that's the case, is it possible for us to prove this? So I almost have that all set by the colors that I wanted. Okay, so now what I'm going to do is I'm going to take this image and I'm going to copy it back over onto our working document, and then we're going to finalize this with some more directions. Alright, so let's hope that works. Let's see how good of a document we got here. Kind of a messy document. Let me try one more time. Hopefully that's a little better. Okay, so here's our object we get to work with. It was a quadrilateral. Any old quadrilateral would do. They didn't really specify anything beyond that. Now we're going to follow some of the directions and see if we can prove why this thing, or even if it is, a parallelogram all the time. So draw and label a diagram representing the statement, which I've done. Then add a diagonal to the original quadrilateral in your diagram. So what we're going to do is follow those directions, and we're going to create a diagonal. It's one of the diagonals from, that doesn't look so good, from our original quadrilateral over to here. So that's following the directions so far. We were supposed to draw a diagonal in the original quadrilateral that we started with. Now write an argument to prove that this midpoint connector, write an argument to prove the midpoint connector theorem of quadrilaterals, which what this is. Prove that it has to be a parallelogram anytime you connect the midpoints of a quadrilateral. So this is going to stretch your memory banks just a little bit, because here's what I want you to focus on. Earlier in this chapter, what we did is we looked at a different theorem that had a similar ring to it. That if we were to connect the midpoints of a triangle, now remember, E was the midpoint of this segment, F was the midpoint of that segment. If we were to connect the midpoints of the two sides of a triangle, then this opposite side was always going to be parallel to this side, and it was always going to be equal to half of the length, or this one's going to be twice the length of the diagonal of the red line. So this one is half the length of this segment here. Okay, so how did we do that? Well, it doesn't take very long to do, so I'm going to do a quick rundown of why that happens to be true. First of all, we know that this segment is the same length as that segment because it's the midpoint, and this segment's the same as that segment because it's the midpoint. And we also know that this angle is in common for, and I'm going to highlight another triangle, this triangle here. And we proved earlier in the unit that those two triangles were similar because they share this common angle B, and their sides are a scale factor of 1 to 2. 1 to 2. So by the side angle side similarity theorem, our green triangle and our yellow triangle are similar. And because they are similar, all their corresponding angles have to be congruent. So that means angle here and the angle here, they have to be congruent because they're corresponding angles of similar triangles. Well, that also is the name of two types of angles that are on parallel lines. If these angles, I'm going to call them just for clarity, 1 and 2, are congruent because they're corresponding angles of similar triangles, they also have to be corresponding angles on these two lines, the dashed line here, dashed line there. And if corresponding angles are congruent on two lines, then that forces the lines to be parallel, and that's what we learned as the PLP, the parallel line postulate. If corresponding angles are congruent, then the lines have to be parallel. So we now know that this line here is parallel to that line there. So if those two lines are parallel to each other, I've now got a pretty good basis for how this is going to end up proving that it's a parallelogram. Because now if we come down here in the other side, and selecting these down here, these two triangles have to be similar by the same concept that we had over there, by the side angle side. Share the angle, sides are in a ratio of 1 to 2. So that means these two triangles in blue are similar, which means this angle is the same as that angle, which are corresponding angles, which forces these lines to be parallel. So now we've got these two lines that have to be parallel to each other because they're parallel to a third line. All right, so that's kind of the basis and premise of what we're going to do. And then clear that out. There's nothing saying that we couldn't have drawn this diagonal this way. Let me try to get this swung around down here. And then we'd have exactly the same thing. Now, I'm not going to go through all the work again because we used to have this, we already proved it, so we know that if we connect the midpoints of a triangle, then this side here has to be parallel to the bottom side of the triangle. That was called the midpoint connector theorem of triangles, bringing back an old idea. And the same reason, the triangle up on the top, the red one has to be congruent to, that red one, because we connected the midpoints of the triangle, this line has to be parallel to this line by the midpoint connector theorem. They're always going to be parallel in half the length by this concept of midpoint connector theorem. So kind of went a little bit a long path to get there, but now let's go ahead and formalize what we're going to do with this in its entirety. First of all, what we're doing is we're given that we have a quadrilateral A, B, C, D. Step 1 is given. Step number 2, what we did is we drew a diameter, and we got BD is a diameter, or diagonal, diagonal of our quadrilateral. And that was given. In step 2, what I did is I recognized that EH has to be parallel to BD. EH has to be parallel to BD by the midpoint connector theorem of triangles. Again, keeping in mind that when we find the midpoints of any triangle, then if we connect those midpoints together, this midpoint connector has to be parallel to the base. And then we're going to do the same thing on the top. Step 3, we know that FG has to be parallel to BD, again by the midpoint connector theorem of triangles. So if EH and FG are both parallel to the same line, then they have to be parallel to each other. So EH has to be parallel to FG, and one of the things we could probably put in that is by substitution, property of equality. So now we know that those are parallel. We've got half of our work done. And then, as you saw in the previous one, what I did is I took and drew the other diagonal. So now I'm going to flip it around again, hopefully. There, lets me do it. We're going to come right back and use that same old concept we got done doing with the midpoint connector theorem. So now I know that EF is parallel to AC, and I know that HG is parallel to AC by the midpoint connector theorem. So in step 5, I know that EF is parallel to AC, and I also know that, I'm going to write it in the same step, HG is parallel to AC as well. And that is through the midpoint connector theorem of triangles. In step 6, since they're both parallel to AC, EF has to be parallel to HG, and we'll use our substitution property of equality again. And now what we have is the fact that these two sides have to be parallel as well. So if we have two pair of opposite sides that are parallel, then in step 7, the quadrilateral EFGH is a parallelogram by definition of parallelogram. So kind of a unique method of proving that. It was through our midpoint connector theorem of triangles, through the idea that those triangles had to be similar by our side angle side similarity theorem. But once we have that in place, it really simplified quite nicely. And now we're able to verify and prove that it has to be a parallelogram.